You know about the states of matter. We learn them in school. They're solid, liquid, and gas. A rock is a solid. Water is a liquid. The air you breathe is a gas. The particles in a solid are packed tight. They hold their shape. In a liquid, they're looser. They can flow and take the shape of a container. In a gas, they're flying all over the place. They expand to fill whatever space they're in. Then you might learn about plasma. It's the fourth state. It's like a gas, but the atoms have been ripped apart. Electrons are stripped from their nuclei. It's a soup of charged particles. The sun is made of plasma. So is lightning. It's the most common state of matter in the universe, even if it's not that common here on Earth's surface. So we have four: solid, liquid, gas, plasma. It seems neat and complete. A nice set. But what if there's another one? Something totally different. Something we interact with every single day, but we don't think of as physical. What about information? It sounds strange. Information isn't something you can hold. It's not a rock or a glass of water. It's the words on this page. It's the music coming from your speakers. It's the genetic code in your DNA. It's the 1S and OS on a hard drive. It feels abstract, not physical. How could it be a state of matter? This isn't just a philosophical word game. A growing number of physicists are taking this question seriously. They are proposing that information is not just an abstract concept. They believe it is a physical entity. And if it's physical, it must have physical properties. It might even have mass. Some go a step further and suggest it could be a fifth state of matter. It's a wild idea. It changes how we think about the universe. It suggests that the fabric of reality isn't just made of particles and energy. It's also made of bits and data. To understand this, we need to forget what we think we know about information and look at it through the eyes of a physicist. First, let's be clear on what a state of matter actually is. It's a way to describe the collective state of many particles. The transition between states, like ice melting into water, is called a phase transition. This happens when you add or remove energy, usually in the form of heat. Heating ice gives the water molecules more energy. They vibrate and break free from their rigid crystal structure, becoming a liquid. Heat the water more, and they break free from each other entirely, becoming a gas. It's all about the arrangement and energy of the particles. So, for information to be a state of matter, it would need to be made of some kind of particle. And it would need to undergo phase transitions. This is a very tall order for something as seemingly abstract as a bit. Let's get into what physicists mean by information. It's not about the meaning of words or the beauty of a song. In physics, information is simpler and more fundamental. It's a measure of uncertainty. Think about a coin. Before you flip it, there are two possibilities: heads or tails. There is uncertainty. Like, once you flip it and see that it's heads, the uncertainty is gone. You've gained one bit of information. A bit is the most basic unit of information. It's a choice between two options: yes or no, on or off, 1 or 0. The physical world is full of these binary systems. An electron can have a spin that is up or down. A photon can be polarized horizontally or vertically. Each of these is a physical system that can store one bit of information. So, information is not some ghostly thing. It's always encoded in a physical state of a physical system. You can't have information without having something physical to represent it. The pattern of ink on a page, the magnetic alignment on a hard drive platter, the state of a subatomic particle. The idea that information and physics are linked is not new. It goes back to the 19th century, with work on thermodynamics. Scientists were studying heat and energy. They came up with a concept called entropy. Entropy is often described as a measure of disorder. A messy room has high entropy. A clean room has low entropy, but a more precise definition of entropy is related to information. It's a measure of the number of possible microscopic arrangements a system can have. Imagine a box of gas. The atoms are whizzing around randomly. There are countless ways you could arrange those atoms that would still look like a box of gas. This system has high entropy. Now imagine a crystal. The atoms are locked in a perfect, repeating grid. There's only one way to arrange them to make that specific crystal. This system has low entropy. High entropy means many possibilities, which means you have little information about the exact state of any single particle. It means high uncertainty. Low entropy means few possibilities, which means you have a lot of information. The link is inverse. More entropy means less information. Less entropy means more information. This connection between the physical concept of entropy and the abstract concept of information was a huge breakthrough. It was the first hint that information was a physical thing. The real bombshell came in 1961 from a physicist named Rolf Landauer. He was working at IBM thinking about the fundamental limits of computation. He asked a simple question: does it take energy to compute? Specifically, does it take energy to erase a bit of information? His conclusion was profound. Landauer's principle states that erasing one bit of information must, at a minimum, release a tiny amount of heat into the environment. This is a fundamental law. It doesn't matter how you build your computer, whether it uses silicon chips or tiny billiard balls. The act of erasing information has a physical cost. Why? Think about what erasing means. A bit can be a 1 or a 0. Let's say it's stored in a computer memory cell. Before you erase it, it's in one of two states. You don't know which. After you erase it, you reset it to a known state, say 0. You've gone from 2 possible states down to 1. You have reduced the number of possibilities. You have reduced the system's entropy. The second law of thermodynamics says that the total entropy of a closed system can never decrease. So if the entropy of the memory bit went down, the entropy of something else must have gone up to compensate. That something else is the surrounding environment. The only way to increase the entropy of the environment is to release energy into it as heat. So erasing a bit creates a tiny puff of heat. This was revolutionary. It directly and unbreakably linked a logical operation, erasing a bit, to a physical quantity energy. Information wasn't just an abstract idea anymore. It had a physical consequence. Doing something to information meant doing something to the physical world. This is the cornerstone of the argument for information being physical. If information is physical, does it have mass? This is where the idea gets even more interesting and controversial. This brings us to a physicist named Melvin Vopson. In recent years, he has been the main champion of the idea that information is not just physical, but that it is a distinct state of matter. Vopson starts with Einstein's famous equation, E=mc². This equation reveals a deep equivalence between energy E and mass m. Mass is a form of concentrated energy. Energy has a mass equivalent. Vopson then brings in Landauer's principle. We know that erasing a bit of information releases a certain amount of energy, so he reasoned, if a bit of information has an energy equivalent and energy has a mass equivalent, then a bit of information must have a mass equivalent. He calls this the mass-energy-information equivalence principle. It extends Einstein's work. It suggests that the 3 fundamental quantities in the universe are not just mass and energy, but mass, energy, and information. They are all interchangeable. According to Vopson's calculations, the mass of a single bit of information is incredibly small. At room temperature, it's about 10 raised to the power of 38 kilograms. That's less than the mass of a single electron. Measuring something so small is completely beyond our current technological abilities. But Vopson goes further. If information has mass, what is it made of? What carries it? He theorizes the existence of a new elementary particle, which he calls the infon. Just as photons carry the electromagnetic force, Vopson suggests that infons carry information. These would be a new class of particle, a candidate for the elusive dark matter that physicists believe makes up about 27% of the universe. Dark matter is a mystery. We can see its gravitational effects on galaxies, but we can't see it directly. It doesn't seem to interact with light. Vopson's hypothesis is that dark matter could be made of infons. The universe is constantly creating information. Every event, every interaction creates new information about the state of the system. If this information has mass, then over the 13.8 billion years of the universe's existence, a huge amount of information mass could have accumulated. This could be the missing mass we call dark matter. So now we have a complete picture of the eye's argument. Information is physical Landauer's principle. It has a mass equivalent Vopson's principle. It might even be made of new particles infons. This leads to the ultimate conclusion: if information has mass and takes up space, it can be considered the 5th state of matter. What would this state look like? Vopson suggests it would be a bit like a solid. In a solid, atoms are arranged in a fixed ordered pattern. This low entropy state can store a lot of information. He envisions a universe where, at a fundamental level, everything is built from bits of information. In this view, particles like electrons and quarks are just incredibly dense collections of information. The other states of matter, solid, liquid, gas, plasma, are just different arrangements of this fundamental information substrate. Another place where information gets disturbingly physical is around black holes. This is the famous black hole information paradox. According to Stephen Hawking, black holes are not completely black. They slowly leak radiation, now called Hawking radiation. Over immense periods of time, this causes them to evaporate and disappear. Here's the problem. The laws of quantum mechanics are very strict about one thing: information can never be destroyed. It can be scrambled, hidden, or rearranged, but the total amount of information in the universe must be conserved. So, what happens to the information of all the stuff that fell into the black hole? A book, a star, an astronaut, all of that has a specific arrangement of particles. That arrangement is information. When the black hole evaporates, does that information just vanish from the universe? Hawking initially thought it did, which would mean our understanding of quantum mechanics is wrong. Most physicists today think the information must somehow get out. But how? This paradox has tied physics in knots for decades. The debate forces physicists to treat information not as a footnote, but as a central physical character in the story of the universe. It must be accounted for. It behaves like a physical quantity that needs to be conserved, just like energy or momentum. This lends huge weight to the idea that information is a fundamental part of physical reality. So the case for information as a physical thing seems strong, but is it a state of matter? This is where many physicists would draw the line. There are powerful arguments against this idea. The main counter-argument is that information is a property of matter, not a form of matter itself. Think of it this way. A block of iron has properties like temperature, mass, and volume. But we don't say temperature is a state of matter. Temperature describes the average kinetic energy of the atoms in the block. It's a property of the system. The iron itself is the matter, and its state is solid. The critics would say information is the same. Information describes the arrangement of particles. It's a description of a state, not a state itself. A hard drive stores information. But the information isn't a separate substance floating inside the drive. It's the specific pattern of magnetic domains on the physical platter. The matter is the metal platter. The information is its configuration. You can change the information by changing the configuration, but you haven't changed the fundamental stuff it's made of. Another major issue is the lack of direct experimental evidence. Vopson's mass-energy information equivalence principle is a theoretical proposal. His calculated mass for a bit is so fantastically small that there is no experiment we can currently design to detect it. The infon particle is purely hypothetical. Until someone can devise an experiment to measure the mass of a bit or detect an infon, the idea remains in the realm of speculation. Science requires evidence. Without it, even the most beautiful theory is just an idea. The concept of a phase transition also poses a problem. We know how to turn a solid into a liquid. You add heat. How would you melt information? What does a liquid state of information even mean? Or a gaseous one? States of matter are about the collective behavior of many particles and the distinct phases they can exist in. It's not clear how the concept of information fits into this framework. You can have one bit of information. You can't have one molecule of liquid. The very definition of a state of matter relies on a collective system. It seems like a category error to place information in the same list as solid, liquid, gas, and plasma. So, we have two very different ways of looking at this. One side says information is physical, has mass, and is a fundamental building block of reality, potentially a new state of matter. The other side says information is just a property, a way of describing the arrangement of ordinary matter, and calling it a state is a misuse of the term. Maybe there's a third way to think about it. Maybe the problem is our old definitions. The idea of states of matter was developed in a world we could see and touch, a world of rocks, water, and air. But modern physics has shown us that the fundamental nature of reality is much weirder than that. At the quantum level, particles are also waves. They can be in multiple places at once. The universe might be a hologram projected from a lower dimensional surface. In this strange new world, maybe we need new categories. Perhaps information isn't the fifth state of matter. Perhaps it's something more fundamental. The physicist John Archibald Wheeler coined the phrase "it from bit." This is the idea that every particle, every force, every bit of physical reality derives its existence from bits of information. In this view, information isn't another state of matter alongside the others. It's the foundation from which the others emerge. A solid is just a particular computational pattern of bits. A liquid is another pattern. The universe itself could be seen as a giant quantum computer, and everything we see is the result of its ongoing computation. The fundamental laws of physics are the algorithm. This is the school of thought known as digital physics. It suggests that at the very bottom, the universe is discrete, like the pixels on a screen. You can't zoom in forever. Eventually, you hit the fundamental unit of reality, a single bit of information. If this is true, then information isn't a state of matter. Matter is a state of information. This completely flips the question on its head. It's a radical departure from traditional physics, which assumes that matter and energy are the fundamental things. It's an exciting and mind-bending possibility, but again, it is highly speculative. We have no way of proving that the universe is a simulation or that space-time is made of discrete pixels. So where does that leave us? Is information the fifth state of matter? The honest answer is we don't know. And it depends on what you mean by state of matter. If you stick to the traditional definition, a collective phase of particles like a solid or liquid, then the answer is probably no. Information doesn't seem to fit the definition. It behaves more like a property that all matter has its configuration. But if you are willing to expand the definition to think about what the fundamental stuff of the universe might be, then the answer becomes a lot more interesting. The link between information and energy is undeniable thanks to Landauer. The puzzles of black hole physics force us to treat information as a physical quantity that must be conserved. These are solid pieces of evidence that information is not just in our heads. It's woven into the fabric of the cosmos. Melvin Vopson's work is pushing this idea to its logical conclusion. By proposing that information has mass, he's making a testable prediction. It's a long shot, but if he's right, it would be one of the biggest discoveries in the history of science. It would confirm that the universe is made of mass, energy, and information. Right now, this is the frontier of physics. It's where deep questions are being asked. What is reality made of? What is the relationship between the physical world and the abstract world of data? Asking whether information is a state of matter forces us to confront these questions. It's easy to dismiss the idea as a metaphor, but the history of science is filled with ideas that started as metaphors and ended up as literal truths. The idea that the Earth moves around the sun was once a strange computational trick. The idea that matter is made of tiny, indivisible atoms was a philosophical guess for 2,000 years before it was proven. The idea of information as a state of matter might be in a similar stage today. It's a hypothesis, a new way of organizing our understanding of the world. It connects thermodynamics, quantum mechanics, cosmology, and computer science. It suggests that the line we draw between the physical world of things and the informational world of ideas is not as clear as we thought. Even if information isn't officially crowned the fifth state of matter, this line of inquiry has already been incredibly fruitful. It has given us a deeper understanding of the physics of computation. It has sharpened the questions we ask about black holes and the nature of reality. It forces us to see the universe not just as a grand machine, but as a grand database, a system that is constantly processing information. Think about the DNA in your cells. It's a physical molecule, a long string of atoms. But what makes it special is the information it carries. That information is the blueprint for a living being. The physical structure of the molecule serves to store and protect the abstract sequence of data. The matter and the information are inseparable. Or think about the human brain. It's a 3-pound lump of wet biological matter. But it generates consciousness, thoughts, memories. These things feel like pure information. Yet they are the product of a physical process, the firing of neurons. Change the physical structure of the brain, and you change the information it produces. The universe seems to work this way at every level. Matter and information are two sides of the same coin. You can't have one without the other. Whether we call information a state of matter is a question of classification. It's about which box we put it in. The more important truth is that information is physical. It's as real as a rock, as real as a star. It takes energy to erase it. It takes up space to store it. It has to be conserved. It may even have mass. So maybe the next time you download a file or read a sentence or simply look at the world around you, you can think about it differently. You are not just observing matter and energy. You are observing information. You are observing the countless bits that describe the state of every particle, every field, every galaxy. And you are left with a profound question. Is this information just a description of the universe, or is the universe a manifestation of information? Yeah, we don't have the answer yet, but the search for it is changing everything.